Hello, everyone. Welcome back. If you are in the overflow, hopefully people will move over. We are going to continue our afternoon, the final talk of our first session on planning and reasoning with Professor Leslie Kaelbling from MIT CSAIL.
All right, thank you. So thanks for inviting me here. I couldn't resist a very brief story about my history with Yale. So when I was first here, I was actually thrown out for being drunk and disorderly. That's a fact. And then I came here and had a job interview, but that didn't work. But so now I'm here, and so I'm happy for the invitation. Okay, so good. So I do robots, and my goal is to make a robot, to understand intelligence. I would like to understand intelligence at a level that encompasses, humans and robots if I could. And so I want to figure out how to make a general purpose, autonomous, intelligent robot. A jack of all trades, maybe, master of none. So, when I think about this problem, I say, well, okay, there's engineers and there's data, and somehow we have to put engineers and data together to do this job. Engineers are too inarticulate to just write the program. You can't just use data. I think you can't just use data. So then the question from the engineering perspective is, how do we design the engineering processes so that they're efficient in all the measures that we need them to be efficient in, and so that the robots perform well in the world? I have to say, I've been messing with my talk in the back of the room, because I usually talk to an audience that has a whole totally different set of bought-in assumptions than I think this room does. And so I've done a little bit of changing around of that, but not all of it. So forgive me if I'm preaching to the choir in some parts of what I have to say. Okay, so I want to think about this problem for a minute, right? Which is, okay, I want to be the robot factory. I'm not going to worry about the hardware part, just the software part. I'm going to make robots, and the robots are going to have to go out in the world and perform well. And so the question is, what should my objective function be as the robot factory? And so, okay, I have to find a program that goes in the head of the robot that maps its history of observations and actions into its next action. And so if you come to me with and you tell me a distribution over problems that these robots are going to have to solve, right? A distribution over houses that they're going to have to go to, or niches that they're going to have to survive in, then there's an optimal program that could go in the head of those robots, the same program in the head of all the robots. It will learn if it needs to learn. It will do estimation. It will, whatever you want, there's an optimal strategy. Okay, so in a way, I've written down the math that solves my whole problem, and I could just go home. On the other hand, we have no idea really how to instantiate that. The title of my talk was Rationality, so we can say, all right, if I'm going to approach this problem, I can say, well, that robots are supposed to perform well at expectation in their world. That feels like a kind of rational criterion. So one way to approach the problem, and I would argue the really prevailing paradigm in my world, is something like this, right? So you say you want the robot to work in a bunch of environments, great. Make a simulator or a suite of simulators that simulate those environments. Make as general purpose a learning method as you possibly can, with the least touch that you can possibly make. Couple it to the simulator, run it for absolutely ever, and get out that best robot program for that situation. So it seems cool, right? And there's not very much baked in, and it's an optimization process that's happening on the evolutionary scale. So maybe evolution does something like this for you. I am skeptical about the pragmatics of this as an engineering method. Right now, in a way, we know evolution did a pretty cool thing, but it had a lot of resources, and maybe I am insufficiently patient for that. So I'm going to pursue a different line. Okay, so how do we get to be sample efficient? Well, we need bias, right? So we know that if you can build in a machine learning situation, if there's just a Pareto front involving structure that's built in and data. And so if you build in some general stuff, then that buys you out of supplying a lot of data. So what are the things that I'm willing to build in to my robots? What do I believe about my world? I don't know. I believe we exist in a 3D physical world made of things and stuff. Okay, most of my colleagues don't even want to go there. Okay, the effects of the robot's actions are sparse and local, right? So I can fling this remote around and it's not going to bother the people in the back row. And the users are going to make highly variable demands on the robot, right? So I'm interested at least in the case that's not the case where I need to train a robot to fold a particular kind of napkin in a restaurant or weld a particular model of a car that's going by, but actually the case where the demands are considerable. So if you make different assumptions, you should build in different bias. But I would like to take these three things as given about the kinds of systems I want to build and then see where we go from that. So, okay, so rationality, you guys know about rationality. Okay, I don't have to talk about that. So we're going to have a belief about the world state, think about models of the effects of our actions in the world, and think that in some sense what we derive from the user's desires is some kind of a utility function. And so then we can make a factory, our factory can make rational robots, where the factory, when it does learning, can build in rationality as a bias. And furthermore, those robots, when they're out in the world, they will do some kind of reasoning, maybe some kind of explicit reasoning, and also be able to leverage that bias in the learning that they do in their world. Okay, so let's think about cognitive architecture. We already had a great conversation about cognitive architecture. I mean something slightly different by that phrase, but it's okay. So again, if the prevailing view in the world right now is roughly that this is what your cognitive architecture should be, so that there's just some goo in between the sensors and the effectors, and then you train it up and it becomes a thing. I'm a little more of an old school engineer. I have a particular set of boxes and arrows. It doesn't really matter what they are. I'm not committed to this one in particular. But I feel like I need one. Like I feel like I need to think about modularity. What are the pieces and parts? What kind of algorithms, what kind of computation goes in them? Because I think that they don't all need the same computational structure. And I have fun talking to Nancy, for instance, about this. And like it seems like brains that do different stuff in different places, and they're not all wired up the same. So that gives me, I don't know, some amount of I hope that maybe that this is a sensible approach. So I'm always just waiting for my cognitive science colleagues to tell me like useful things like what is the type of stuff on the arrow that goes from perception to reasoning. But so far I don't know what the answer is, but we could talk about that later. Okay, so let's say I'm going to go down a road in which I have architecture that looks, I don't know, sort of like this. We could talk about it later if you want to. So this used to be, I mean, people have drawn pictures like this for a long time, but it's been really hard to instantiate. But recently, all the deep learning stuff has really made a bunch of things better. One of the things that's just changed my life is the improvements in perception. So from a single image, in this case, it's an RGB and depth image, but you don't even need that anymore. From a single image, you can get a lovely segmentation. You can make completions of what the shapes are like and so on. So I can work with that just really very well. Okay, so then there's this question about planning. So should you do computation online in your head while you're embedded in the world versus have a feed-forward function that just produces the reaction, right? And there's all kinds of good computer science reasons to argue that that planning is an important strategy, that online reasoning. And again, this used to be an argument that I had to make really hard, but now a lot of people are bought into the idea that online reasoning is a good idea. So I think it is. But then the question is maybe what should the model be that we use for planning, right? So if you want to say, oh, I'm going to do planning, you say, okay, the world is in some state. I'm going to take an action. What will happen, right? I need a model like that. I need a model of the effects of my actions. So then the question is, what should that model be like? It used to be called a transition model, and now it's called a world model, which is okay. We want it to be learnable efficiently in terms of data. I think it's important that it be incrementally learnable and updatable and somewhat local, right? So if you teach me to be really good at knitting, it doesn't make me forget calculus. And it's efficient to reason with, right? So there's a bunch of design criteria for that model. The canonical early thing was to try to do it from images to images, and in fact, there's a ton of work on world models right now. If you say world model, people will think you mean video world model, which means a very beautiful 30 frame per second ability to generate movies of things. It requires a lot of data, and it's also hard to plan with. Oh yeah, video world model. So you could say, oh, okay, I'm going to compress my representation and do learning in the compressed representation. But I want to think about, we had to talk about symbols. So I want to think about symbols, right? So we might be able to say, look, I have some low-level controllers, some policies in the world that change the low-level state. This picture is inspired by George Conadaros, who was one of my postdocs a while ago, who liked to talk about the swampy state and the crispy state. So this is the swampy state. This is the continuous world all around you. And the question is, it's really hard to reason down at that level. So then you'd like to lift up to something a little crisper, right? You'd like to say, oh, okay, there's some set of states such that if I run this controller for a while, I'll end up in these other states. And so the question is, can we learn to carve nature at its joints, right? Can we find the places where things are almost independent? They're never going to be completely independent. No factoring is going to really be right. But maybe we can find ways of pretending that aspects of the world are independent. So we can do this kind of from the neural network perspective. People talk about disentangled encodings, right? Which would say, oh, I'm going to take my state and divide it into chunks. And then ideally, I would like to train a thing that's sparse on the chunks, right? So I say, okay, actually, the new value of this chunk depends only on a couple of the previous chunks. Or maybe most chunks don't change their value most of the time, right? So if I can start thinking about the factors, the pieces of the state, the position and orientation of this remote and whatever the person in the back corner is thinking about, they're probably not, they're coupled a little, but not maybe super coupled. Then I can learn a much sparser, I can learn a model with fewer parameters. Another piece of leverage for factoring, for disentanglement, for finding ways of talking about pieces independently, is to understand the world in terms of objects, right? To say, oh, actually, this world, there's a remote and a podium and a laptop and so on. And objects can serve as indices into a disentangled representation. Right? So I could maybe represent my state of the world by saying, oh, I have a whole bunch of objects and each object has some properties. Right? So that's good. And I can talk about the relationships among the objects and so on. And eventually that can lead me to a kind of representation of a model which is a cousin of a graph neural network in a way, but where roughly you can learn something like, if A is on B and I move B, then A probably moves too. And I can learn that in generality, not about any specific A and B, but just with a quantifier. So that would be, in my language, a sparse lifted factored transition model. You can also write these things down in text, right? So maybe it looks more like, it could even be a probabilistic description of how the world changes, or maybe just deterministic. But what's important is you can build representations that have some discrete structure. They're discrete in the sense that they talk about objects, they talk about particular properties of objects and relations of objects, but where we can use neural networks to compute the new values, to recognize whether the objects do or don't have that property, and so on. So it's what some people would call a neurosymbolic representation of how things work in the world. Okay, so I'm going to pursue a little bit using and learning these kinds of models for problems on robots. All right. I am not going to go through all these things, but I'm going to show you a thing. This is Josh's current favorite thing. I don't know if Josh is in the room at the moment, but it's okay. Yeah, okay. So here's a robot, and we wheeled some stuff up in front of it, and it's looking at the scene, and it was told to do something in natural language, and it's going to do the thing. Okay, so the thing about robots is that actually you look at this and you think, well, fine, a 4-year-old could do that, so why are you so excited? But the answer is, for robotics, this is pretty good. It's pretty good. Because, he just wheeled that thing up there. It wasn't like the objects weren't put in rigid jigs. And okay, so the robot looked at that scene. So the question is, how does it work? So here we go. We get one image. We get an instruction. We run through all the cool image processing methods that we have now. We run those things through some other trained neural networks that, for instance, can predict good ways of grasping an object, sort of affordance models. We throw that stuff into a task and motion planner. So it's a search-based inference algorithm which uses representations of the way that the world changes that are like those causal action models I showed you, and that generates a plan. So, here's an example. Put the coffee pods onto the tray. And what's important about this is that we didn't tell it to do anything with the Coke can, but it understood that in order to put the coffee pods on the tray, it had to move the Coke can out of the way. So it's doing actual, real reasoning about 3D space and where objects can go and stuff like that. People in robotics like to make a big deal about cross-embodiment generalization. That's another word for it works on a different robot. And the way you get cross-embodiment generalization for us, so if you're very data-driven, then you need a pile of data on the new robot and so on. We have to give it a URDF, which is like just a description of how its joints are put together, and do a quick camera calibration, and then it can do a thing on a different robot. So that seems good. And, it can do, you can add new skills to it by engineering. I mean, we added, but it was just given the goal of like having the board be clean and the marker be in the bowl or something, or everything in the bowl. So I could do that. I'll show you one more, which is kind of fun. So this is a head-to-head comparison of our thing called TipTop and Pi 0.5, which until about 6 months ago was the best. It's still the best openly available, completely data-driven controller, which has exactly the same input and output as our system. It was trained completely on data, and it starts right away because it doesn't have to ponder. Our thing is still thinking. It had to do with the perception, and now it's thinking. That could be made faster if it weren't graduate students doing the implementation. They're lovely graduate students, and they're very good, but it's just, half time for two guys. But you can see that, like, taking a minute to figure out what's going on before doing the thing, at least for right now, works a lot better. It's kind of incredibly entertaining. I could show you lots of these movies, but okay. So this is just some argument that, like, the deliberative view it used to be seen as completely infeasible because it seemed way too slow. It seemed like the requirements on the perception were too difficult, that it would be just too hard to describe how the robot works. But really, the thing that's important is that you just get this incredible generalization. Like once you have a thing that works, it just continues to work, and you don't have to retrain on new situations. So again, this guy is flailing around. Okay, so that's an example of what you can do deliberatively. So now I want to talk about learning from demonstration. So another big paradigm right now at the moment in robot learning is learning from demonstration. So I want you to just watch this demonstration, and I want you, while you're watching the demonstration, think about, if I asked you, please do that for me tomorrow in a different scene, what that would mean. Like, how would you think about it if I said, could you do that for me? Okay, somebody want to tell me in natural language? What is it? What's the job, do you think?
Sort things by their shape.
Sort things by their shape, yeah. Is there maybe someone have another candidate hypothesis there?
The fruit bowl and the utensils.
Fruits in the bowl, utensils somewhere, yeah, good. Okay, so good. So right, so what I want to say is, okay, everybody's doing learning from imitation, but what should you learn from a demonstration? So most of the work going on right now is going on at a very low level of abstraction. So at the level of trying to imitate a trajectory, you could try to imitate the robot's trajectory in the global frame. That maybe clearly not good. Robot trajectory relative to the salient objects in the world. The thing that most people are trying to do is learn a policy that maps hand camera images to velocity commands. That's what you saw the previous thing doing. You could try to learn how the objects move, where the objects ended up. You could try to learn what the human wanted, right? So there's many different levels of description, and it's really interesting to think about how you actually, if we think about engineering a system like this, like what is it that its objective should be? We've been having fun with the last, well, okay, and what it can be depends on what you already know, right? So if you don't know anything, if you don't know about picking objects up, or that utensils are utensils, or you don't know anything, my joke is that then all you can learn is a trajectory. Like if you don't know anything, all you can learn is a trajectory. And maybe that's good for waving a wand, right? Because you have no theory of wand waving, so you have to actually just do Wingardium Leviosa and get it right. But if you understand anything about the world and the effects of your actions on the world and what it is that somebody might want, then you can learn something at a higher level of abstraction. And if you learn something at a higher level of abstraction, it will generalize better. Yeah. Okay, so that's the thing that we've been working on, under the assumption that the demonstrator is a rational agent that is trying to do a thing, and they're acting not optimally, but near optimally, then we can do a Bayesian thing. I'm not going to go into the details here, but I'm going to show you just some examples, right? So how this works is, while we're doing the demonstration, we use all that perception stuff that I showed you already to construct a pretty good 3D model of what's going on in the world. And what we're looking for, and we're going to use LLMs for this, I'll show you, what we're looking for is what we call an explanation program. An explanation program is something that takes as input the image, not the image, but actually the 3D description of the scene, like what the objects are and how big they are and how they relate to each other. So it takes that in as input, and it produces as output some goals for a planning algorithm. So LLMs are not good at producing plans for robots. They're not good at telling you what your arms should do, or even what order, even that you need to move the Coke can out of the way in order to put the pods on the tray. They're just not good at that. We are good at that. Like, we have algorithms to do this. So I feel like, okay, for the things I know an algorithm for, I'm going to do that. So I know how to solve a planning problem. If you tell me, put this particular spatula in the pot, do this other thing, keep this upright, I can construct algorithmically a plan for the robot to do that. So I'm going to try to map from a scene. So an explanation of what the human wants is going to be a mapping from the scene to a goal for the planner down at a slightly lower level. Okay, I'm going to skip that. Okay, but so there's a Bayesian story. We want to say, okay, we want to find an explanation program such that the behavior that we saw would have been likely if that were the explanation, and that explanation is also likely. And so what we're using is a VLM as a prior, as a way of saying, oh, here are the kinds of things that I can imagine would be reasonable goals, right? It could be reasonable to put the round things in one bowl and the sticks in another one, or it could be reasonable, I don't know, sort by color. It's probably not reasonable to put the things whose dimension is divisible by 3 in the left-hand bowl. It could be a perfectly legal interpretation, but it's not. The VLM is not going to suggest that. Okay, so then we end up with this situation where basically the VLM proposes programs, so you can think that as a kind of a prior. We use a planner to say, if that were the explanation, what's the behavior that we would get? That helps us evaluate the likelihood of the behavior that we did actually get given the planner. We do it hierarchically so it's more efficient, and eventually we get out that explanation program. I'm not going to show you in detail, but I'll just show you this one more example, right? So this is an example. Again, this is all the training data. So 3 training examples, no words. It's teleoperated. So students teleoperating the robot. So this is the training data for a particular task. And then having seen that data, we infer that program, the best explanation seems to be put the utensils in the pot upright. Upright. The robot does some awkward things. It would have been easier to put them in blade down, but because it would have been easier to put them in blade down and it didn't do it, upright is a better explanation. That comes out in the math. So yeah. Okay, so that's kind of good. So we could do learning from explanation, from demonstrations very data efficiently by leveraging what we already understand about the world and what people might want. I'm going to skip a couple of things and talk about, oh, okay. Oh, why does this always start playing before I'm ready? Okay. Yeah, okay. So I'm going to talk about how we can learn those causal action models. So far I said we can use causal action models to do planning. If we can plan, why? If, okay, we'll just let it go. If we can do planning, then we can understand demonstrations. The question is, how do we get these models, right? Okay, so we've been thinking about how to do that. And so here's a case where, oh gosh, these things have some bizarre life of their own. Okay, I don't know what to do about that. I'll just go back. Okay, so here's a system that tries to learn causal action models. And it's given demonstrations not of a particular thing we want, but just demonstrations of like how stuff works in the world. The assumption, big assumption for right now, is that it already has low-level controllers that can do the things. So those are built in already, the motor control stuff. And so, okay, so it's given some demonstrations of doing things. And the demonstrations are labeled according to which controller ran between the different scenes. And then the idea is, from that information, we would like to learn a causal action model. Okay, so, and the reason we want to do that is because we get extreme generalization, right? So we can generalize from Nishant walking around with an iPhone showing himself doing things in the world. If we learn how the world works, if we learn a causal model for the world, then we can put those things together to solve new problems. In this case, on the robot who was told that the table should be wiped off. And so it is going to go and wipe off the table. Go, robot. Okay. Okay, so I'm going to tell you just an idea about how this learning could go, because it's totally different from gradient descent. Just to have, many people have forgotten that there's other ways to do learning, even though this is somewhat old school. But okay, so imagine that we have a bunch of action sequences. So state, action, state, action, state, action, state, action. In this case, the actions are calls to motor controllers, so they're not like really low-level actions. And we look and we see, okay, there's several times we did action 1. So I'm going to go grab the data that's just about having done action 1 and look at the state that came before and the state that came after and try to learn what A1 does to the world. So I can take S and S prime. So assuming I have a language of predicates, that's a giant promissory note, which I will discharge in a little bit. So assume we have a set of predicates that describe states of the world. I can write down a description of the world state before and after in terms of the predicates. I can look at the ones that changed and focused on those, because that's what we're assuming, that the changes are sparse and we're really focusing on the changes. We can group the transitions that have the same actions and effects and turn constants to variables so that we end up with something that's implicitly quantified instead of being about this particular remote. That gives us the symbolic part of the model, actually, already. It says if these things are true and I push this button, then these other things will be true afterwards. And there's some stuff about learning the physical parameters to the continuous valued parameters to the motor controller, which we don't have to worry about. Okay, so that's a cartoon of a story about how you might learn a causal action model. But the question is, if you had predicates, where do you get the predicates? We had some algorithm that tried to generate them from a grammar. It was okay, but not really very good. But now we're using a VLM. Okay, but I think this is awesome. So we're using a VLM not to tell us what the predicates should be, but to help us with the carving the world at the joints problem. It's just, so we're showing a bunch of movies to the VLM and saying, what are some ways of describing what's going on with the objects in this scene? And under the assumption that natural language has come to contain the important distinctions that we need to make about the states of our world, then we're using the model to tell us that. What are the important distinctions that humans have found in describing how the world works? So it generates a whole set of possible predicates. And then we do a kind of search in that space of subsets of those predicates to ask the question, if these were the predicates that we were using to describe the world, how good of a causal action model could we learn? And we end up with a set of predicates and a causal action model. So I'll show you a couple demonstrations because they're fun. I mean, this is one where now we've moved into a different room. But this is, using the same data that we saw before about emptying out a trash can and erasing stuff. The robot is given the goal, of putting the Coke can in the blue bin, and the eraser should be in the trash can, and the table should be clear. So this is the other leading brand. So this is a purely data-driven strategy. It tries to dump the eraser out of the bin. It doesn't work. It tries to pick up the Coke can. That doesn't work. It knocks over the trash can. Now it has the eraser, but in the bin. It's okay. So that doesn't work. And our thing does. We probably don't need to watch more robot movies. It's kind of like watching toddlers. Robot people love watching their robot movies. One more example. Here's a juicer, right? So this is a very fancy juicing machine. I don't know, you could put a fruit in the top of it, and you don't have to do anything else. And juice, you just have to turn the knob. Juice comes out one side, and everything else comes out another side. Okay, so this is the demonstrations, right? So we get like 3 demonstrations that show stuff like how you turn it on, how you put a fruit in the top of it. There's some other demonstrations that show where you have to put the cup to get the juice to come into, and where the cup goes that the pulp goes into. We run it through that process with the VLM suggesting the vocabulary. We learn this model. It's not exactly perfect, but it's not terrible. And it says roughly if you have 2 cups and they're empty and they're in the appropriate places with respect to the thing, and there's a fruit in it and the lid is closed, then if you turn the switch, you'll get juice in your cup. So then in a new world, right, so the important thing, the thing that I really care about is generalization. Now in a new environment, which is not where the demonstrations came from. It was asked for pear juice. It didn't do pear juice before, but the VLM can understand what a pear is, and so it figures out that there's pear. It puts the pear in there and does the thing. It has to go get the other cup. So the thing that's important here is it's not slavishly reproducing a demonstration. It never had a demonstration of this particular arrangement at all. So now it's going to actually turn the machine on and make pear juice. It does spill a bit. But okay, so good. So I am skipping 2 things, but we have ways of learning to reason more efficiently. And we have ways of reasoning about what we do and don't know about the state of the world. I think that's important. I'm going to talk about one more robot thing and some to-do items, and then take questions. Okay, so one more thing. So this is an example of the mixture of learning and reasoning, right? So here the view is, let's imagine that. You ordered a robot from me, and I sent it to you, and it has built into it some basis set of skills. And you've asked it to do some tasks, and maybe it hasn't been so good at doing those tasks yet. And so what it's going to do, if it has some time, is practice. But it's going to practice rationally. So it's going to go and gather data, but it's going to gather data that it kind of really thinks is important for what it needs in order to learn. So here's the example setup. So this is Spot again. We tell Spot to put the ball on the table. Spot looks around, finds the ball. I gets the ball, puts it on the table. Poor Spot. It's a drafting table. Nobody told Spot that. So it's going to try again, and it doesn't work. Okay, so now that people, wait, did I skip something that I didn't mean to? Okay, no, all right. Okay, so now people are upstairs asleep. Spot's downstairs saying, oh man, I have to do a better job tomorrow. And so it's going to try to practice. It will practice the skills. It has 2 different skills. In this case, it knows about putting the ball on the table. It knows about putting the ring on the table. It knows about putting the ball in the ring. Why are my videos not cooperating? Okay, I'm not sure. Okay, so it tries a couple more times with the ball on the table, and it's estimating whether it's getting better at putting the ball on the table. And it wasn't getting better at putting the ball on the table, and now it thinks maybe it would be better to put the ring on the table and put the ball in. But put the ring on the table, that didn't work either. Oh, okay, but this time I put the ring on the table and it worked. And it's learning that it's better to put the ring over on that side of the table and to put the ball in. So yay. So now it has an example of a thing that's going to work. And now it's going to practice for 3 hours, actually with only battery changes, trying stuff out and learning how things work. Okay, I'm not going to do this in detail, but eventually, anyway, it will learn. It will learn to put the ball on the table, the ring on the table, and the ball in the ring. What's important is that it's reasoning about which skills it has that are important for the thing it's trying to do, how it is that the sort of experiments that it does are likely to improve its model. And the important, again, just to kind of emphasize why it's important to be reasoning, is that you can be persistent, right? Because it's always just saying, well, I don't know, this thing went over here, but let me make a plan to make it sure. So good. I wasn't going to talk about this, but then I thought, well, okay, but I've been kind of going along for a long time complaining about the idea that we have enormous problems to solve. The problem of living your life is very long horizon. There's too many objects. How in the world could you put that in a planner? And instead of trying to make the planner get bigger, the way I think about it is trying to make the problem get smaller. And I don't know, I think of it as a dynamic abstraction formulator, but you could think of it as a metacognitive model on the fly. I forget the name. Model synthesis architecture. Right. Okay, good. So I think that this is an important idea, and we've done some stuff at various times. Something about predicting which objects in the world are important to us. Something about doing temporal hierarchical decomposition of the problem and deciding whether it's okay to treat two subproblems as sort of serializably independent versus whether I have to solve them all together jointly and so on. Okay, so I'm going to wind down now. So rational agents and large pre-trained models. I think we want to use large pre-trained models in the factory part of this. We want to use them for perception. We want to use them as a general repository of facts. My own sense, at least at this moment, is that they're not the best thing at doing inference, and maybe we can use algorithms for inference and build small models on the job for the inference algorithms to solve. Yeah. So there's a bunch of questions. Partial observability is a thing I care deeply about and I haven't talked about. What do we do about memory for space and objects? What does the robot's eye tell the robot's brain? What's the information flow to and from perception? What are the queries? What are the answers? Who makes them? At what rate? And how do we make sure that all the learning can happen over the lifetime? So with that, I will say thank you and take questions.